being recorded, and it will be available on our website as well as our public-facing YouTube channel. And so you will have access to that in the next week or so once our admin team can get that uploaded. So thank you all for joining. I'm now going to hand it over to Dr. Jess Wild. You're an assistant professor with the Department of Biostatistics and like you have all
Research
of these
associate.
research associate. Okay. A research associate, and you're affiliated with multiple departments. So I will let you give your introduction. And today we are going to be covering mapping in R. And I'm very excited because I am going to be learning a lot today too. So without further ado, Dr. Wild.
Yes, thanks so much for the great introduction, Lauren. So as Lauren mentioned, I work as a research associate within CETA, which basically means that I'm a PhD level statistician who focuses a lot on collaborative team science work. I personally am mainly working with the Department of Emergency Medicine with some of their sort of global health and trauma medicine studies. But I did a lot of my PhD training in more of the clinical trial design sphere, as well as briefly touching into some more advanced data visualization, including some mapping. So today's topic is definitely something that I am really excited to present about today. I think geographic and spatial visualizations are a widely underutilized tool. They have a lot of versatility, a lot of customizable options, and just generally are a really cool way to make your data a little more concrete and add some context in terms of what is changing over both space, potentially over time, and how do we sort of contextualize the information that we're trying to present in a way that readers or collaborators can really understand in more of a geographical context. So today I'm going to be mainly presenting R code to do different types of example figures. Any of the figures I'm presenting today could very easily be customized for more specific data set or research questions. So my goal today is sort of to give you all the tools that you need to customize visualizations to your specific context, because there are literally an infinite amount of spatial visualizations you could create with R. Many of which are very similar. If you've ever used GIS software, you can get a lot of the same effects, but in a more open source, freely available coding language, which is very cool. So let me just share my R screen. Yeah, so this is the RStudio code I'll be working off of today. Just to double check, is everybody able to see the screen? And I can easily zoom in if the font is too small. Okay. So today, I'm just going to briefly go over some of this is just sort of the data sets I'll be working with. I am a bird watcher, so I got some geospatial data on bird migration statistics and counts. You could easily do this with more public health focused data sets. This is just one that I have available and always enjoyed working with. And then we'll also be doing some more complex visualizations at the end, looking at some elevation maps of volcanoes and some pollutant monitoring station data. But those will be more of an advanced challenge, an extra bonus challenge at the end. So for the first thing that I want you all to know for working with map figures in R is it's really important to pick a good base map and to make sure that your data set is well set up to be compatible with R's geographical software systems. So for R, a lot of what we'll be working with is sort of defining different spatial polygons. One of the ones that is really commonly used for a lot of research is looking at the US, sort of contiguous US data. So this is sort of code that you would use if you wanted to graph some of the states of the US. And then this is what that mapping would essentially look like. So this is sort of, in my opinion, one of the very, very most basic possible visualizations you could have, where we're just laying this nice base mapping. And then what we do after that is sort of layer more data features on top of this. But this is sort of just the very basic way that we might visualize something in R. We could also very easily choose a different style of base maps. One of them would be more of an elevation style, so looking at some of the geographic features of this map itself. And then that one So this is sort of the code that you would use to get that elevation information. This one, I'm pulling it from the data set that I had pre-planned, so it's specific to that data set. And then we're just sort of defining a boundary box and then mapping what the elevation itself would look like. One thing to know about spatial visualizations in R is they almost always take a bit of time to run just because the computational intensity is pretty high. Anything spatially related, there's a lot of individual points that the computer system is working through, especially as you get to more complex data sets. So hopefully everything today is going to run live. If it doesn't, I made backup plans, so we might be switching screens to that. But for now, this is sort of what that more elevation focused mapping might look like. And just in general, I'm going to be using ggplot for most of these. If you're familiar with ggplot, I think one of the other presenters either this week or last week is going to go into more details on that. But it's a great visualization software system in R, and I would say 9 times out of 10, when I'm doing any sort of visualization, it will be ggplot based. But this is sort of a different type of base map figure where instead of having those just like the state mappings, we're now looking at more elevation style data where we can see the Rocky Mountains, a little bit of the Appalachian Mountains, and then everything in between. You would use different base maps depending on what you're trying to describe in your specific data set. I think these two I don't use as commonly, but the next two I think are the ones that I tend to use when I'm personally doing visualization, which would be thematic maps and then leaflet maps. So thematic maps is essentially something where, again, you're going to be defining your boundary box. This is just saying what are the dimensions spatially that we're going to be looking at this map. Today, I'm mainly looking at the United States. You could easily define it for any other geographic region, as long as you know approximately what the boundary points of that region are. And then we also set the coordinate reference system. This is sort of a very safe standard one. Depending on the context you are specifically working on, you might look at something a little bit different. I don't think I've yet had to use anything besides the basic reference system. But then after we sort of define this boundary box based on our data set, I'm then going to like map this, use the tmap package to sort of use their OpenStreetMap view. And then that creates graphics that are more like this, where it's a little bit more like what you might see in a lot of geography textbooks or things like that, where it's very much looking both including some geographic features of the landmass, as well as a lot of those typical like state boundaries and some basic some of the larger cities. And one of the cool things about TMAP is if you zoom in more, and here I'm going to move to one that's Colorado specific, it does get a little bit more specific where you can also see some main metro areas as well as some roads, and then just something that's a little more detailed. So, and then the fourth option is leaflet style background maps, which I think one of the sort of cool features of these to call out is their interactivity. So these maps allow a lot of really interesting zooming features. I like using these a lot as my sort of baseline when I'm figuring out a new data set or I'm not quite sure what I want to visualize, just because they do give you, as the analyst, a lot of options for really working with your data in a more hands-on way. So this is what those maps look like. They're very similar to me to sort of if you've ever seen those Google satellite images. And a lot like those images, you do define your boundaries for the view that you want to look at. But the cool thing about leaflet maps is you can also do a lot of interactive zooming and sort of move around the map itself, all the way to the point where you can pretty much look at anywhere in the world within that one visualization. And then some other interesting features of these maps, and this works for the other styles as well, but you can also layer multiple baseline maps on top of each other to some extent. I think typically what I've done and seen done is people will often take one of these more thematic or leaflet style maps and then add on those state boundary polygons on top of them. So that way we have both sort of an idea of like what does the region's geography look like, what are some interesting features, as well as having those like reference boundary lines. So those are sort of four potential options for what I call background maps. I don't think of these as visualizations in themselves so much as it's sort of like your canvas for which on which you sort of draw the visualizations. These are all great options for for if you're starting out with just picking a style of map that fits what visualization you're trying to look at. But then what we would do after that is try to add on our specific data set, our data set specific visualization tools. And this is sort of where the main focus of today's talk is going to be on taking those sort of background maps and then looking at how do we overlay our data set features and characteristics in a way that both is accurate as well as allows us to sort of tell the story of our data and really visualize interesting features. And there's obviously many different ways you could do that aspect as well. I'm first going to present what I like to call sort of raw point maps, where we're saying we're taking our data features and we're overlaying them as points on the map. There's a lot of other different options and customizations you could do, but this is sort of like a good basic to start with. So the data set that I'll be working with for this section is looking at observation counts of bird data. Specifically, I'm going to be looking at some that is counting up screech owls. So just to go in detail on what we'll be mapping, the first layer of our map is this sort of GMSF, which is telling the ggplot to add essentially essentially add dots for each of it's essentially telling ggplot like we are looking at specifically these SF style geographic maps. We're telling them like what our aesthetics are. Right now, I'm looking at sizing the points by how many species counts there were for that observation, and then coloring them by the various different types of bird species. And this is obviously specific to whatever you're trying to visualize. This was just the most natural iteration out of the data set that I'm working with. And then after we sort of define those very, very basic properties, we're then looking at adding some state level polygons for context. Here, I'm just, again, using that like state polygons that we defined further up, and then just sort of telling R how exactly I want those represented. And then sort of the output of that map. And here I'm using, again, a very extremely basic level background map. I think for this one, it was literally just the state polygons. Reiterating that these take a lot of time to run just because they are so sort of computationally intensive. But essentially what we're doing here is we're defining first how we want our data to be represented. And then our second layer is we're defining the state's boundaries. And the reason I did the data first is because I want those boundary lines to show up on top of them, versus if we'd done it the other way around, essentially the boundaries would have been obscured by the data points. And then which layer goes on top versus which is used as a base is going to be dependent on your visualization and what you're trying to show. But here, what we have is essentially species counts, where the different colors represent different species. If you're interested, the red is for eastern screech owls, the green is for western screech owls, and the blue is for whiskered screech owls. I definitely know too much about birds, but for this visualization, we're also varying the size of the points by how many individuals were counted. So for any observation row in this data set, we could have multiple different individual birds counted. So that sort of adds these two additional layers of information on our map. And something to keep in mind whenever you're doing these types of visualizations is you want to sort of balance competing ideas of we want to keep our maps as simple as possible so that the people who are reading them or interpreting them don't get confused or overwhelmed by information. But we also want to include as many layers of sort of essentially visual encoding as we need to get to fully convey all of the information. And especially if we're thinking about making these types of maps for like a journal submission, we also have to deal with a lot of space constraints if we only get so many figures. So the more information that we can reasonably and readably include in each individual figure, essentially we'll be able to tell a more nuanced and deeper story about our data set. But those are sort of the two ideas that we always have to think about anytime we're working with these sort of spatial visualizations, is we want a simple visualization so that's understandable, but we want a nuanced visualization so that we can include as many different features as possible in order to tell like in order to accurately represent the data. So that's sort of one way to represent this data set. And then another way that we might think about it is maybe we look at this data set and we say, that's a great visualization, but it's really hard to pick out some of these data characteristics, so there's just too much going on. Like for me, I'm having a hard time finding these blue whiskered screech owl points just because there's so many of the other colors present here. So another thing we could do is we could stratify our analysis, which, if you're familiar with stratification, just basically means we sort of split our analysis into different pieces. So here, what I'm doing, and I'll let this run while I explain, is again, we're using that same basic information of this is the data that we're visualizing. We're using a spatial analysis, and then we're layering the polygons on top of that. But the really interesting, the difference in this figure is we're also using facet wrap, which is a ggplot function. And we're saying, which creates essentially individual panels, so multiple figures. And we're saying we want those figures sort of split apart by the species. I know this is small. Sorry, if you were in the wild, you would probably do this as sort of an HTML document, so it would show up larger. But essentially what this map is doing is it's showing the same data points, the same coloring, the same scaling as our previous map, but this time we're breaking it apart. So this is just eastern screech owls, this is just western, and then this is just whiskered owls. So to me, this is something that I would look at if I was trying to understand how these different species were separated geographically, because it gives us a much more readable interpretation for this third grouping, where we can actually see where they are since they're not being covered by these green points. But again, it depends on what we're trying to visualize about our data set, because there's definitely contexts where we might prefer the previous map because it showed where they are in context of each other. But just those are sort of two very basic versions of a spatial visualization map looking at essentially count data over geographical space. So the next type of map that I'm going to be looking at is just looking at raw point maps with a different sort of background style. If you remember, I showed you about 4 different background mappings. We could use any of those 4 with these types of visualizations. They would all work. It just depends what we're trying to convey about the data set. So this example is similar, except it's using that elevation style mapping. So this will also be showing our points over space. We're also looking again at that owl data. The difference would be here we're using a geom raster because we're working with elevation data. So the background map that we have, once it finally renders, is going to look much more geographically grounded instead of being sort of determined by just the state boundaries. And this is what that one would look like here. We do automatically get this helpful little visualization legend where it's showing, depending on the color of the background map, that's how you know what the elevation is. And then these black points are going to be all of those observations. Here I've kept it a little more simple. It's not scaled by how many observations. It's not colored by species. Personally, I don't think I would typically use an elevation style background map with this data set, but there's definitely data sets that we might want that information in. It all depends on what context you're working with and what you're essentially trying to say with that particular figure. And then this would be an example of what it looks like with a thematic map, which again is those maps that show more of the sort of more of the state boundaries as well as some significant like roads or city features, but are also looking at certain geographic features as well, like land, like all of the like lakes and waterways. So this one, it uses different basic colors, and you can tweak any of these color settings you want. Essentially, as long as you know the code for the color, you can change it at will. And it's also using that size discrepancy of the points to indicate like how many individual birds were counted there. But this is just sort of the T-map representation of that same data set. I like this one a lot just because I think it's really clear while also giving context. But again, it's sort of a judgment call in terms of what base map works best for what data set. And then lastly, we're going to look at those interactive leaflet maps with this data set, where again, this one, the coding to get them is a little more complicated just because these maps have a lot of different customization options. And anytime you have more customizable figures, they also tend to mean more complicated code. But basically what this is doing is that we're first specifying our background map, which is that essentially like just the base surface that we're visualizing over. We're defining the boundary box, which is where on that interactive zoomable map are we trying to look first. And then we're adding state polygons. And finally, we are adding circles for each of those observation points. And this is sort of the way that you define the color and the color here and like the size fill of those circles. And there's a lot of ways to change each of these individual elements depending on what you want. But this is sort of what that looks like at scale. And then again, the cool thing about leaflet plots is you can sort of zoom and in and out at will and sort of drag the map around. And that's still true after you've added the points. So if I wanted to really zoom in like on the East Coast here, because there's a lot of data points, I very easily could do something like this where I'm looking specifically mostly at Pennsylvania here. Um, and then you can sort of drag it around wherever you want to. And if you want to click on specific points and see like the value they represent, you also can. So like that dot there that I'm clicked on, it's telling me what species that is, as well as the count specifically. That's why leaflet plots are so cool, is because they have that interactivity elements. And there's a lot of extra versions that will do different things that I won't cover here, but I strongly recommend looking into these anytime you want more customizable graphics. They're really great. So that's sort of our first style of maps, which was these sort of setting a base map, adding any contextual polygons like states that you need, and then placing dots on the map to represent the different data points. And then the next style of maps is a little bit different. This is the one I tend to see most often when people are starting to play around with visualizations, just because I think it's very common. It's very easy to understand in context. And this is choropleth maps. I'm only about 75% sure I'm pronouncing that right. I've actually never heard it said before, but essentially what these are is they take geographic regional boundaries and then summarize information within each of those regions. So for today, I'm going to be using the US states as my sort of unit level regions. I've also often seen this done with different countries or specifically with different census tracts. A lot of visualizations in public health will try to tie sort of something like asthma rates within census tracts to maybe pollution monitoring data, that kind of thing, where we're looking at those sort of smaller levels of geographical units so we can look at sort of distributions across like a state or a region or something like that. Those are very cool. I've chosen to keep it a little bit simpler today, so we'll be looking at more state level maps. But this is sort of an example of what those types of maps could be. And this is very much an extremely basic version, but essentially what you have is for each of these defined geographic units, like for us, that would be states, we're summarizing information across the unit. So here what I've done is I've essentially added up like how many individual bird counts do we have within each state, and then use that to assign a color gradient where essentially the lighter the color gets, the more species counts were found within that state. And I believe this one I averaged over the entire year of 2024. And you can play around with how long, like what the scope of the averaging is. It depends very much on context and on what you're trying to visualize. But here, that's what that represents. So the way that we would read this here is say in Montana, we had a relatively low number of observations in 2024 versus here in Texas, we had a very high number of observations. And there's a lot of different color gradients you can choose. I really like this one, and I think it's appropriate for the Valentine's Day week that we're in. But there's a lot that are a little more presentation or journal friendly. But that's sort of what choropleth maps look like. And the way that we would tell ggplot that we want that style of visualization is essentially we're passing in our data set here, and then we're telling ggplot that yes, we want this sort of SF style geographic map. And this is how we're filling the different pieces of the map. So this is saying that our total count numbers is what's going to determine the color that fills in each of these pieces. And then after that, this is where we're specifying like what color gradient we use. I really like using our color brewer, which is a package because they have a lot of non-basic, more customizable color gradients to choose from than what you get in R. I believe the R basic is sort of or blue to green to yellow, which to me, I just don't like that visual style. Um, but color brewer is something that I like to give people whenever I'm talking about map style visualizations, just because it has a lot of these sort of scaled gradient colors. So ways to represent visuals that we're saying every point exists somewhere along this scale, and we're using color to represent like where we are, which is why when you look at Texas, that is visually different from like Maine over here. And that the degree of visual difference in color is indicative of the degree of difference within the data for both of those regions. But that's sort of how you would code a very basic version of these maps in R. If you wanted something that's a little bit more interactive, a little bit more concise, you could also think about potentially animating a figure. So looking at maybe averaging everything over the entire year is too much summarization. Maybe we're missing trends within the data set itself. Like I'm really curious if why Texas is so different from Montana or why Texas is so different from the rest of the map. And I want to see, does that change over time? So I might think of something like an animated graphic where we're looking at essentially instead of averaging over the year, maybe we do it by month so we can track how everything changes. And that's also a really cool separate branch of graphs in R is animated graphics. I bring them up with maps because I think maps are a way that's really interesting to see how data is distributed over space. But animations also let us see how that spatial distribution changes over time, which can be really powerful in a lot of contexts. This is one of the map visuals that is very slow to run. So just know whenever you do an animation, it's going to take some time. I'm hoping it'll run live here. If it doesn't, I do have saved versions that we can look at instead. Ah, it looks like this is actually going to work live, which is amazing. I haven't done this one before. But this is sort of what that animated graphics view looks like, where if you watch, we have this sort of counter that's telling us where we are in time. Here I've just done different years, but you could easily do it a little bit more granular, like over the month or the week. But this is sort of the measurement of how is this data changing in time. So looking at the spatial distribution in 2021 might be very different from the one in 2022, and as we go so on and so forth further out in time. But one thing to note is that we are using the same static color gradient to define differences. So if you compare over years, they are comparable. Like within this graphic, everything's comparable, both between states as well as between time frames. So just to go into some of the details of how you would go about generating that graphic, because I know that's something that tends to intimidate a lot of people when they start looking at these sort of spatial plots. Essentially, there's two steps to any animation. First, you're going to define each individual, like the format by which the ggplot generates each individual visualization, and then you define how it sort of zips them together into a single animation. So in order to define each visualization, I'm again using ggplot, passing it the data set, the same sort of like telling it that we want a spatial visualization map, telling it what we want, what variable within the data set we use to define the color of each of those states. And then one thing that's important that I want to call out for everyone here is this is the line of code that makes sure that the color ranges are comparable across plots. So essentially, if you didn't have this line of code, what you'd have is 4 different plots that each have their own color range. So within each of those sort of slices of the animation, everything's comparable, but it's not comparable between slices. So you couldn't take the color of Texas in 2020 and compare it to the color of Texas in 2024 and make reasonable statements about the differences because we really need to set that, we need to make sure we're specifically telling ggplot that we want it to be comparable between plots. And that's what this statement does. We're saying we're setting a limit that the range of our color, or essentially the range of our color scale is determined from the entire data set. So it's not within each year, it's from our entire data set so that everything is sort of comparing apples to apples instead of apples to oranges. And then after that, it's just this statement here is what's defining how we split apart our data into the different animated images. So here I've done the animation off of years. So I created a variable in my data set that says like this is the summary information for each separate year. And then I'm specifically telling ggplot that that's what we're using as a transition marker is the year here. And then one thing, in order to get that nice little label that tells you what year it is, this is the syntax we would use there, where this part is going to be changing over the course of the animation, where this is where you'd say, like it would say 2020 or 2021, etc. But once you've set all of that up, this is essentially this piece of code here defines each individual slice of the animated visualization. So this can be used to define the visual for 2020 all the way up into 2024. So creating those 4 separate plots. And then this piece of code from the GG Animate package is how you define, like sort of how you bring all of those separate plots together and make sure they're animated correctly. So obviously, I kept it pretty simple. There's a lot of ways you can tweak this. The most important one to note is this end frames, and this FPS is looking at how many total frames and like how quickly you're switching between frames. Here I set an FPS of 10, which means essentially there's 10 frames or there's I think 10 seconds per frame is the way that Animate works with it. I don't do these graphic images a lot, so if you're working with these specifically and you want something more customizable, I highly recommend looking at some of their documentation. And then you can also try to define height and width, depending on the context you're working with. I know sometimes RMD documents are a little picky, where that can often cause issues, so you want to make sure like whatever output you need, some of these like individual pieces can be very important. But then that's essentially how you would go about animated graphics is first defining the framework for each individual slice and then sort of knitting them all together in one. So those are some of are my 2 main versions of more sort of basic to intermediate geographic data set visualizations, where we looked at, first of all, choosing base maps. And then after you've chosen a base map, are you visualizing points, in which case there's a lot of different options for that, versus here visualizing summary information over geographic regions. So those are the main 2 pieces that I want to make sure we covered today. And then next, I'm going to be covering sort of more of an advanced or more statistically complex topic, which is spatial interpolation maps. This isn't necessarily something I expect everyone to be able to do themselves in R. I think this is one of the cases where we're looking at visualizations off of more modeling, more prediction and inference modeling type analyses. So it's a little more complex. I think when thinking about what topics to include this project in this presentation, I do really think this is important to understand just in terms of interpreting these maps and being able to sort of having access to some of the different possibilities within this visualization space. So interpolation maps, basically what you are looking at there is creating smooth surface geographic visualization. So instead of having those like base map and then we put dots or polygons on top of it, what interpolation maps do is they're saying we have data from various different places within a geographic region. So we have these sort of discrete points where we have observations, and we're trying to understand based on those points, can we extrapolate or interpolate what's happening at all of the places that we don't have specific observations. So some of the examples that I'll be working with are I think first I'll be looking at an example of a volcano data, where this is one of the data sets that's just freely available through R, where they have different measurements of the elevation of a volcano at different points along within that defined boundary region. And then the interpolation comes in terms of, well, we have these elevation data at specific points, but we don't know what exactly the elevation measurements are between the points, but we can use a model to try to predict those elevation and then take the modeled predictions as well as our observed points and create a smooth surface visualization. Basically, what that looks like, I'm not going to run all this code live because the modeling aspect does get quite time consuming. Um, but I think what I'm going to do is show you the visualization and then we can work backwards in terms of understanding how we get there. So the map that we get out of this is something like this, where here, essentially what we have on this map is this sort of arbitrarily defined boundary box around a volcano. And then this, like the color gradient is showing us the elevation. So this is actually one of the examples where elevation style maps make sense if we're trying to understand geographic features. I know that's not something that we all probably do in our own research space, but I do think there are cases where that could be useful information. And there are sometimes we do care about these sort of elevation style graphics. They're also much easier to explain in presentations, which is why you'll see them a lot. But essentially, this is saying that the lighter the color is at each point along the surface, the higher the elevation is. So we can see it does visually look like a volcano. Like this is the ground around it. Then here is sort of the mountain part, and then this little darker dot is probably like that dip within the volcano itself. So that's the main sort of interesting thing about these interpolation maps is because we don't have information on elevation at all these points. We have information from like a select group of points within this graph, and then we're modeling the rest of them so that we have a complete sort of smoothed out picture of what our elevation looks like. So the very, very much SparkNotes version of how you would do these interpolation graphics. Again, my sort of main goal here is just to make sure that we can all understand these when we encounter them, not necessarily that you would all be able to take this code and recreate it for your own data sets. Is first you're defining the grid over which you're predicting points. Fun fact, the sparser the grid, the faster your visualization will run, but the less detail you might potentially get out of that visualization. So it's always sort of a trade-off between, do I want really sharp feature lines on my visual, or do I want something that can run without leaving my computer going for very long amounts of time? Also where parallel coding gets really, really useful. But that's essentially what we're defining here is this is the grid over which I want to predict points. And then what you do is define this sort of varigram measurement of how similar observations are depending on their distance from each other. Obviously, there's a lot of really complicated mathematical assumptions and calculations that goes in here that I'm not going to get into a ton of detail on. But essentially, this is sort of like your model of what is the spatial dependencies between points. Because if we have like a point here, a point here, and a point here, we're essentially, if we want to predict a point here, we're saying like, how far is it from point A versus point B versus point C? And based on all of those distance measurements, how similar is it to all of their elevation measurements? Sort of what is the predicted dependency matrix, essentially. And then you would then like sort of fit that model in code like this. And then after you have your sort of spatial dependencies set up, you would apply a sort of interpolation model. Here I'm using Kriging, mainly because that's just the one that I'm most familiar with. There are other options and various ways to make this much, much more complicated. But essentially here you're sort of spatially modeling all of the various locations that you have data from in order to fill in all the blank spaces at the points where we don't have those measured pieces, those measured observations. And then after you are finished fitting both of those model pieces, the output is going to be data for like that smooth surface. I think I can show you guys what this data set specifically looks like. Let me find it. Yeah, so it looks something like this. That's a little. So it looks like this in the very most basic versions, where it has these sort of predicted numbers, as well as like these are the XY coordinates that tell us this is exactly where that point corresponds to on this map. Obviously, there's a lot of complex mathematics behind all of those pieces, but that's sort of generally how we would go about creating these smooth surface interpolation maps. And again, this is one that's more just a general example. It says, I don't think this comes up a lot in sort of health data context. But oh, and this is sort of the code for how we would essentially visualize all of those sort of interpolated points, where again, we're passing our data set, defining what we want as our aesthetics, which is XY being like these are essentially the coordinates along the axes. And then this is the predicted value that we're visualizing here. And then there's a lot of sort of more not tuning, sort of like tuning characteristics where we're just telling it we're working with a raster style, raster style data, raster style visualization, and then setting some aspect ratios. And finally, looking at this is sort of defining the color mapping, which would be this piece here. But that's sort of the very, very basic version of an interpolated map. And then the next example I'm going to show you is something that's a little more relevant to us, just because I think it does a really good job of helping look at some more complex visualizations that I think are a little more realistic or a little more relevant. Again, there's a ton of complicated modeling that goes on behind this. I think, again, I'm going to show you the visualization itself, and then we can talk about how each piece works. This is another animated visualization. Where here I'm actually looking at this data set that we'll be visualizing is looking at pollution monitoring data within Colorado. Colorado actually is used for these types of visualizations a lot just because it has a lot of really great data publicly available. All the data we're using today is something that you could easily grab for yourself and do visualizations similar to this. For now, at least, it's publicly available. Yes, I'm hoping that this is going to run. If it doesn't, I do have a backup version. Again, anything visualization of spatial data related takes a long time to run. Interpolated maps and smooth surfaces in particular take a long time just because we are trying to essentially visualize all of these individual points. I'm going to give it like a minute to run, and then if not, I will switch over to my saved version. There it goes. So while that's rendering, sort of the data set that I'm working with here is looking at pollution levels at various monitoring stations, which are sort of spaced out over the state of Colorado. So we have specific measurements at various individual points. But what I wanted to do with this visualization is say, can we then interpolate what the pollution levels are at all of the points in Colorado that don't have a monitoring station? So again, it's taking that sort of spatial modeling approach where we're working with a finite set of data that we have and trying to then create a smooth surface visualization that shows us trends across the geographic region. And what I've done for this visualization here is I've drawn these sort of black circles around each of the points where we do have those data monitoring stations. And then I'm also sort of marking out when the pollution levels spike. So when they're in their top 10%, you'll see these reddish dots like that. So that's sort of saying like, and this is sort of animated over time. I've done it weekly over 2024. You could easily make it more summarized than that or more individual. That was just a convenient way I found to look at this data set. So this is sort of something we would think about visualizing if we were trying to say track trends over time within space. Spatial interpolation maps are great for that because they allow us to sort of look at these smoothed out pictures of what's going on at various points based on our data sets individually. Like if we had just done this map with the points that we have actual observations for, we wouldn't really be able to pick out a lot of these trends that are changing both over space and time, just because it's hard to see it at that level. The trade-off being the fewer points we have, especially in some of these more far out region, the less certainty we have over the interpolated values. But that's a conversation for an entirely different presentation. But just to briefly go over some of the code of how this style of visualization is created, and it is similar to the previous, that volcano version. First, we're defining our grid over which we want to interpolate and smooth points. That's defining like what are the boundaries here and here. And then you are going to essentially format your data so that it's spatially compatible. Fit that variogram defining what are the dependencies in space. So saying like, if we have a point here, we're looking at interpolating from all of these known observations, and that's sort of the variogram defines like what that relationship looks like within the mathematical model. And then fitting the Kriging model to say like, after we have defined those dependencies, we're going to interpolate our individual observations at all of these non-observed points. And then finally, this is sort of the code to define like what are those hotspots of pollution. So the like little red dots like there. I just did the top 10% because it was a very easy number for me to code. And then finally, this is the visualization code itself. It is pretty long for this one just because it's more complex. I'd say this is a visualization example where we're layering at least 3 different things onto one visual, where we have our original sort of these smooth surfaced visualizations. We're also layering on these points marking where we have our monitoring stations. And then we're adding on our hotspot information for where exactly the pollution is highest. And then I guess a fourth layer would be the animation where we're saying we're looking at all of those trends, but tracking them over time. So basically this is what we would use to tell ggplot that we want this sort of style of visualization where it's a smooth surface. We're looking at these points, which is the circles, where we're saying we want you to add a point at each of the monitoring stations. And this is how we're sort of defining the size and the color there. Adding different geometric figures on top of existing visualizations is sort of a whole branch of spatial options that I really like working with, just because it allows you to sort of layer on a lot of information into one plot in some really interesting ways. And then something similar we're doing with the hotspots, where we're again saying we want you to add points at any part of the surface that had a hotspot identified. And that's a little bit of a different style because we want them here to be red and they're a little bit smaller. But overall, that's kind of how you would do that. Those are sort of 2 examples of how you would layer on additional points and features on top of an existing map. And then here is how we're sort of defining the transitions. Here I'm doing it by week. But that's sort of generally how we would plot that kind of a figure. And then again, the animation code, which is saying for all of the various weekly visualizations, we're now combining them together and defining how quickly it changes and all of that. So that's sort of the overall view of visualization in spatial data that I wanted to get to today. So what we've seen overall is we looked at the different base maps you could potentially use. That's not an exhaustive list. There are others, but I think those are a good 4 to start with, just to understand like what are some of the general possibilities. Then we looked at those more point map style features where we were essentially figuring out what base map we wanted and then adding points on that base map based on the data. Then the third style of maps we looked at was these choropleth. Apologies if I'm mispronouncing that. It's a very weird word, but these choropleth maps, which are saying we are defining specific units of geographic summarization. And within each of those units, for us, it was states within the US, we are going to use a color scale to represent differences in data. And then finally, what we looked at was that sort of bonus, more complex, more statistically intensive version, which was spatial interpolation maps. The overall thing to take away from that section is just that we can use R's ggplot style visualizations to look at those smooth surface visuals from various models, which gives us a lot of different things to play with in terms of creating these very complex, very relevant spatial visualizations. I know we're at about 5 minutes to time, so I wanted to leave a little bit of extra room for questions. I think I'm going to stop it there. If anyone wants me to go to any of the individual maps again or explain any parts of the code or ask any sort of general questions, please definitely do so either in the chat or just shout it out on the Zoom link.
Awesome. Thank you so much, Jess. This was very helpful. I learned a lot today. So if anyone has questions and does not want to unmute themselves, please place it in the chat. Otherwise, feel free to raise your hand and ask your questions. We have a bit of time to do so.
I'm going to stop sharing just so I can see everything, but happy to show code if it's needed.
Well, if no one has questions, I do have one quick question for you. So you were using base maps that are for the United States. So if we were looking at maps that included other countries or at a different polygon, like census tract or something like that, where would you recommend we start to get that information?
That's a great question. So I know R, in the same way that I pulled sort of the state polygons from R, I know they have similar polygons for certain other countries. I think they have it at least for Canada and Mexico. I believe Europe should have something similar and potentially other geographic regions as well. I haven't worked with those as much.
Okay.
And then I know for census tract, I believe what I've done in the past is I think the Census Bureau will actually publish their geographic information. I haven't looked at that in a couple of years, so I'm not sure exactly where to point you to, but I know that is definitely something that's published by publicly available. And I think a lot of the data sets that I've worked with that have just had that information already incorporated as well. So there's definitely
Okay.
it's definitely floating around out there.
Yes. Okay. Awesome. Thank you. Well, if there are no other questions, we can conclude the session today. Thank you again, everyone, for joining. I did put in the chat about 10 minutes ago the link to our attendance survey, so be sure to fill that out to be entered into the raffle for today's session. And this recording will be available on our website, and we hope to see you at our last 4 sessions, the remainder of the week. So thank you all for attending today.